Okay, so this video is an introduction to stoichiometry, and the first thing you need to know when we're talking about stoichiometry is what is stoichiometry. So a definition that you need to know is that stoichiometry is the helps us compare mass relationships between reactants and products. And it helps us use those relationships to make predictions, to look at all these things. The big thing you need to know is that with balancing reactions and stoichiometry, this is all about conservation of mass. This is a big key factor here, okay? All right, so the first step in any stoichiometry problem, step number one, it's before step number one, so it's the first thing you need to do is make sure you're starting with a balanced equation. Okay, so we need to make sure we're starting with a balanced equation. Never try to do stoichiometry unless your equation is balanced because you won't get the right answer. And there are a couple other things you need to know, vocabulary-wise. That's mole ratio, which is the conversion factor for moles of any two substances. And remember that when we're dealing with the moles of something, we're dealing with Avogadro's number, which is 6.022 times 10 to the 23rd atoms in this case, or particles. So actually I'm going to say particles there. This is not erasing. There we go. Really, we're dealing with particles. So a mole of something is 6.022 times 10 to the 23rd particles. On the periodic table, so for example, let's say we have carbon. This is the mass of 1 mole. So that's our conversion factor. Remember back to when we were converting between grams and moles. We know that 12.001 grams of carbon is 1 mole of carbon. Okay? So the mole ratio is something you need to know about. And the other thing is the molar mass, and we've been dealing with that. So your two big vocab words, two concepts you need to understand are the mole ratio, which is a conversion factor between the moles of two substances, and the idea of molar mass. So let's look at mole ratio. Let's say we have an equation like 2 Al2O3 in liquid form decomposes into aluminum and oxygen gas. This equation is balanced already, so we're dealing with that. Let's look at the different mole ratios we have here. So these numbers out front, just like in balancing, are your coefficients. They tell us about the number of moles. It could also represent molecules as well, but it cannot represent atoms. All right, so in this equation, we know that we have 2 moles of aluminum oxide going into 4 moles of solid aluminum and 3 moles of oxygen gas. So the various ratios, mole ratios we have, include that there are 2 moles of Al2O3 for every 4 moles of aluminum. And conversely, just like when we did conversion factors before, we can flip-flop that. 4 moles Al2O3 is 4 moles of Al corresponds to 2 moles, I'm just having trouble here, 2 moles of aluminum oxide. So another mole ratio would be the relationship between Al2O3 and oxygen. So we know that we have 2 moles to 3 moles of oxygen. And notice, in every single one of these, I am indicating the substance that I'm dealing with. And this is very important. You must identify which substance you're dealing with. So the unit here is not just moles, it's moles of aluminum oxide, it's moles of aluminum, moles of oxygen gas. That's really, really important. Okay, so I've got 2 moles of aluminum oxide to 3 moles of oxygen, and conversely, 3 moles oxygen gas to 2 moles aluminum oxide. The last mole ratio that we have here is that there are 4 moles aluminum to 3 moles oxygen gas, or we can write that the other way. All of these conversion factors will allow us to do calculations called stoichiometry. Okay, so let's say that I wanted to figure out how many moles of aluminum I would get how many moles of aluminum would be produced from the reaction I had above if I used 13 moles of aluminum oxide. So my path is that I need to convert from moles of aluminum oxide to moles of aluminum. And the mole ratio that I have, conversion factor or mole ratio that I have for that would be the one that relates aluminum oxide and aluminum, which would be one of these top 2. So if I try that, I start out with 13 moles of aluminum oxide, and I'm going to multiply it by the conversion factor that would get me from moles of aluminum oxide to moles of aluminum. Just like we did when we did conversion factors before, I want to pick the one that has the moles of aluminum oxide on the bottom. So I go back up here, and that would be the 4:2 ratio. So 4 moles aluminum to 2 moles aluminum oxide. And I check my units, moles of aluminum oxide leaves me with the answer of 26 moles of aluminum would be produced in that reaction. So that's an example of how to use mole ratios. Try these examples to show me in class tomorrow. So the first one is, the start examples are ones you're going to have to show me work that you did. So write all possible mole ratios for these reactions. These 2. Write all the mole ratios for these. Okay, so you should be able to come up with, just as a hint, there should be 3 ratios times 2, so 6 ratios for the first one, and 1, 2, 3, 4, 5, 6, 7, 18 ratios, is that right, for the next one? I have to think about this. And 12 ratios, because you should have 3 others for this one, 2 others for this one, and then the 1 other for that one. And if you flip-flop them all, you should end up with the right number of ratios. Okay, so that deals with mole ratios. What if, though, I wanted to find how many grams of aluminum would be made from 26 moles of aluminum? How many grams of aluminum would be 26 moles of aluminum? You've already done those kind of problems, so I'm going to take this a little bit further. What if I had how many grams of aluminum would be produced from 13 moles of aluminum oxide? Remember, our balanced equation is 2Al2O3 gives 4Al plus 3O2. First step is balancing the equation, which I already did, and now we need a plan. We need to go from moles of aluminum oxide to moles of aluminum to grams of aluminum. So that requires 2 conversion factors. If we scan all the way back up to all our possible conversion factors, which you can do in your notes, look in your notes for all those conversion factors, we notice that we need 1 for the relationship between moles of aluminum, moles from aluminum oxide to aluminum, and 1 for moles to grams. So starting with 13 moles of aluminum oxide, my first conversion factor will have moles of aluminum oxide and moles of aluminum. So just like we did before, that's going to be 4 moles to 2 moles. And then you need another one that'll convert from moles of aluminum to grams of aluminum. And it turns out, if you look at your periodic table, that 1 mole of aluminum is 26.98 grams of aluminum. Checking our units, moles cancels moles, moles aluminum cancels moles aluminum, and we're left with 701 grams of aluminum. So your second example that I want to see you do in your notes is how many grams of O2 gas would be produced in the same reaction as up here, from 13 moles of aluminum oxide. Okay, so do that one in your notes and be prepared to show me that in class tomorrow. And that's pretty much what I'm going to do with stoichiometry part 1. Okay, we'll move into stoichiometry, a little bit more complicated stoichiometry Thursday in class. Tonight's homework is going to be to apply these ideas to your mole rockets